In this video, we're going to talk about diode logic gates. The first gate that we're going to talk about is the OR gate. What is the OR gate? Well, let me draw the circuit first. So we're going to need two diodes at two different inputs. So let's call this input A, input B. And this is going to be diode 1, diode 2. Next, we need a resistor, a current limiting resistor, and then an LED, a light emitting diode. And that's going to be connected to ground. Let's use a red LED. Next, we need a truth table. So we're going to have A in one column, B in the second column, and the results of the LED in the third column. Now, 0 means that the input is either off or that its voltage is low. So you can put L for low voltage. A 1 means that the input is on. The voltage might be 5 volts or something. So the voltage is considered high. So let's say if both A and B are 0, will the LED be on or off? Now the ground potential is 0 volts. If both A and B are set to 0 volts, no current will flow through D1 or D2. So the LED will be off because the potential difference between these 2 points is the same. If there's no potential difference, there is no current flow. So this is off. Now what if there's a 1 at A and a 0 at B? So A is on, B is off. So the potential at A is going to be 5 volts, at B 0 volts. So no current will flow through D2 because the potential is the same here. However, we're going to have a current flowing through D1 because current flows from high potential to low potential. As the current flows through D1, it's going to flow through the resistor and then through the LED, turning it on. So in this case, if A is 1 and B is 0, the LED will be on. Now what about if A is 0 and B is 1? In this case, B is on, A is off. So no current will flow through A. But we're going to have a current flowing through D2 because current will flow from a high potential to a low potential. And thus the LED will be on. Now, if both A and B are on, that is, if they're both at a voltage of 5 volts, current will flow through both diodes, and the LED will be on. So thus, we could see why this is called the OR gate, because if A or B is on, the LED will be on. Now, let's move on to the next logic gate. So this is going to be called the NOR gate. The NOR gate is the exact opposite of the OR gate. So we can begin by drawing the truth table. So this is 0, 0, and then 0, 1, 1, 0, 1, 1. So those combinations will not change. In the OR gate, when A and B were both 0, the LED is off. For the NOR gate, the LED is going to be on. For the OR gate, when A and B, for these three options, the LED was on for the OR gate. For the NOR gate, they will be off. So remember, the NOR gate is simply the opposite of the OR gate. Now let's draw the circuit that corresponds with the NOR gate. So like before, we're going to have two diodes. And then we're going to have a light emitting diode and a resistor. This time the resistor goes to ground. the light emitting diode is going to go to the positive voltage source, in this case plus 5V. And let's use a green LED. So this is A, this is B, and then we have diode 1, diode 2. So notice that if A or B carries a 1, the LED will be off. So let's use this option where A is set to 0 volts and B is set to positive 5 volts. Let's see why the LED is off. The light emitting diode typically has a voltage drop of 2 volts. So if the voltage here is 5, this should be 3. Now, this diode has a voltage drop of 0.7 volts if it's a silicon diode. Germanium diodes have a voltage drop of 0.3 volts. So this would be 4.3 volts with respect to D2. Now, these 2 points can be the same. So the higher voltage will take precedence. So if this is at 4.3 and this is at 5, the voltage drop is not high enough to activate the LED. In order for the LED to turn on, the voltage across it must be 2 volts. So because B is on, this voltage will not be 3 volts or less, so the LED is off. So if A or B is at 5 volts, the LED will be off. Now let's see what happens when both A and B are 0 volts. Now keep in mind that the ground is at 0 volts. Because these two are at the same potential, no current will flow through D1 or D2 to go to ground. Because current flows only when there's a potential difference. There's no potential difference between A, B, or the ground. So current can only flow this way, from 5 volts to 0 volts, which means the voltage below the LED will be close to 3 volts. Thus the LED will be on. And thus we can see why if A and B are both 0, the LED will be on. But if one of them is a 1, let's say if this one is a 1, which means it's at 5 volts, and this is 0, then this potential here will be at 4.3. This will be 0. So current will flow through D1, not D2 in this example, but it won't flow through the LED. We don't have the 2 volt voltage drop to activate the LED, so it will be off, even though current is flowing through D1 in this case. So that's the NOR gate. The only way the LED is on is if both A and B are 0. And for the OR gate, if A and B are both 0, the LED is off. So those two are opposites to each other. Now the next type of a diode logic gate that I'm going to talk about is the AND gate. Now the way I like to remember this one is I like to think of it this way. The only way that the LED will be on is if both A and B are on. So that is, if both A and B are 1, the LED will be on. For all other situations, the LED will be off. So that's how I like to remember the truth table for the AND gate. So now let's talk about drawing the circuit. So just like before, we're going to use 2 diodes. But connected in this manner. Now for the 2 resistors, you could use a 1K resistor. You don't want to have too much current flowing through the LED. So if you have a 5 If you have 5 volts across a 1K resistor, it'll push 5 milliamps through it. So across a 2K resistor, that'll push 2.5 milliamps through those two resistors. And in an LED, you don't want it to have more than 20 milliamps flowing through it. So if it's under 10 milliamps, you're okay. We're going to call this A and B. And this is D1, D2. So let's see what's going to happen if A, let's use this option. If A is set to 0 volts and B is set to 5 volts. Let's see why the LED will be off. Well, we know that current has to flow in this direction, or it can flow in this direction. If current flows through D2, then this section has to be 5.7 volts. It has to be 0.7 higher than what we see here. Current can't flow this way because the diode will be in reverse bias mode. So it has to flow this way. But because the voltage here is 5, it can't be 5.7 here. So D2 will be off. Now A is at 0 volts, so that means this is at 0.7 volts. Current can flow from 5 to 0.7 volts. So current will be flowing through D1. D1 is on. Now the voltage at the electric potential at the ground is 0 volts. So notice the potential difference between the resistor and the LED. Across those two devices, the voltage is 0.7. The voltage is not high enough to activate the LED. The LED requires a voltage of 2 volts or more to activate it. In some cases, some LEDs will require a voltage of 1.8, but we're going to stick with a rounded figure, 2 volts. So because we have 0.7 volts across the LED and the resistor, the LED will be off. So thus we could see the truthfulness of that part of the truth table. So now let's analyze this situation where both A and B are on. Actually, before we do that, let's analyze this one where they're both off. If both D1 and D2 are at 0 volts, then this will be at 0.7 as well. So current will flow through both D1 and D2. But no current will flow through the LED because this is still not 2 volts higher with respect to ground. So if either A or B is set to 0 volts, if either of them are off, the LED will be off. The only way the LED will be on is if both A and B are on. So if we set A to positive 5 volts and B to positive 5 volts, then it's going to be on. So because the potential of these 2 points are the same, no current is going to flow through D1 or through D2 because the voltage has to be 5.7 or more to go through D1 or D2. So that's not going to happen. So because current cannot flow in this direction, the only way current can flow is through the LED. Now let's calculate the potentials. The voltage drop across the LED is 2 volts. And then we have 2 resistors. So we have 3 volts remaining. So the voltage drop across the 2 resistors, because they're the same value, will be 1.5. So at this point, the potential will be positive 3.5 volts. And here, the potential will be at 1.5 volts. So we have 1.5 volts across each resistor, but we have the required 2 volts across the LED. So the LED will be on in this case. So that's how the AND gate works. The LED will be on if A and B are on. Now let's move on to the last one. That is the NAND gate. So let's put an N here. Now remember, the NAND gate is opposite to the AND gate. So all we got to do is replace off with on. So for the AND gate, when A and B were on, the LED was on. So in this case, when A and B are on, the LED will be off. It's simply the reverse. So now let's get rid of this. And let's redraw, or draw a new circuit rather. So just like before, we're going to have two diodes. And then after that, we're going to have a resistor go into positive 5 volts. And then we're going to have another resistor go into ground. In addition, we're going to have another resistor which goes to an LED, and that LED connects back to this point. And then it goes to ground. So now, let's see what happens when both, well, let's choose this option. When A is off, but B is on. So A, we're going to set to 0 volts, and B, positive 5 volts. So what happens here? In order for D2 to be on, this voltage has to be 4.3 volts. I mean 5.7 rather, I take that back. This has to be 5.7. So because this potential exceeds 5, that's not going to happen. So D2 will automatically be off. Now for D1 to be on, this has to be at least 0.7 volts, which could happen since this is at 5. Now, notice the potential between the resistor and the LED. So this is at 5, this is at 0.7. We have a potential that's greater than 2 volts, the LED will be on. And so for this situation, if A is 0 and B is 1, the LED is on. Now let me erase these numbers. And let's try the last situation. Let's see when the LED will be off. So both A and B have to be activated. They need to be at a voltage of 5 volts. Because these are the same, no current will flow through D1 or D2. So both D1 and D2 are off. So only this portion of the circuit is active. Now here's the question for you. Is it easier for the current to flow through, well, let's call this R1, R2, and R3? So to get to this point, is it easier for the current to flow through R1 or through R2 and through the LED? Well, we know that electricity likes to take the path of least resistance, and it's easier to go through a resistor than to go through a resistor and a light emitting diode. So this is the path that's going to be easier to take. So if the current flows in this direction as opposed to this direction, the LED will be off. But in practice, to get this to work, we do need to choose the appropriate values of R1, R2, and R3. So it might be best to make R3 2K. Here's why. Let's assume that R2 and the LED are not connected across R1. If we assume that, then these two resistors, they form a voltage divider network. So the voltage at this point, let's call it point C, will be 2/3 of 5 volts. because the sum total of these two resistors is 3K. Keep in mind, to use the voltage divider equation, it's going to be the voltage at point C will be the input voltage, in this case 5 volts, times R3 divided by the sum of R1 plus R3. So it's 2 divided by 2 plus 1, which is 2 over 3. So it's 2/3 of 5 volts. 1/3 of 5 volts is 1.67 volts. So 2/3 of 5 volts, that's 3.33. So this will be set to 3.33, this will be 5 volts when these two are set to 5. Now, once R2 and the LED are connected across R1, the voltage between these 2 points is automatically set to 1.67 volts. That's not enough to activate the LED. We need at least 2 volts to activate it. Now, if this was 1K, this would be 2.5, which may be enough to activate it. In order for this circuit to work, we need to choose the appropriate R3 value. So if R3 is 2K, this will be set to 3.3, and once R2 and the LED are attached to it, it's not enough to activate the green LED. And even if it did, it may be on very, very dimly. But let's assume this is not enough to activate it. It's not the 2 volts that we need. And then the LED will be off. So for this particular circuit, you do need to choose the appropriate values of R3 and R1 in order for it to work. So you want to make sure that the voltage across R1 is less than 2 volts when A and B are on. If that's the case, then the LED will be off. So that's how you can employ the NAND gate using diodes. So that's it for this video. Thanks for watching.